Hey guys, welcome back to CCL Biology, the channel for easy to understand biology lessons. If you're looking for help with general, AP, or college intro biology, then you are in the right place. I am your friendly bio nerd. Thank you so much for tuning into my channel. In this video, I'm going to be talking about pH. So if you want to get a better understanding about pH, then stay tuned. While you're here, don't forget to hit the like button below if you find this video to be helpful. And if you want more easy to understand biology lessons, then be sure to subscribe to my channel and click the notification bell to get updates about new videos that go up every week. Okay, as I said, this video is all about pH. We're going to take a look at how pH relates to water, acids, and bases. And then we're going to talk some about buffers. Now, for starters, pH has the whole background and history that you probably don't need to know. To put it simply, pH tells us how many hydrogen ions there are in an aqueous or water-based solution. Aqueous just means water-based, okay? So let's take that definition up just a little bit. pH tells us the concentration of hydrogen ions in an aqueous solution. Concentration is just a fancy way of saying how many or how much. Now, if you don't know what I mean when I say hydrogen ion concentration, then be sure to check out my video about acids and bases. I'll put that link in the description box below. Now, when we have water or some other aqueous solution that is at equilibrium, that means it's at a temperature of 25 degrees Celsius, and that also means that it's going to have equal concentrations of hydrogen ions and hydroxide ions. Each of those ions is going to be at a concentration of 10 to the negative 7th moles per liter, which together is going to give a total ion concentration of 10 to the negative 14th. So let's take a look at what we've got here. So here I have my little glass of water, and these little guys here represent H2O. We have the oxygen and the two hydrogens. Now, in water, H2O is going to break apart in small amounts to give us hydroxide ions here, which is the OH. And here we see this is actually hydronium, which is H3O. Essentially, the hydrogen ions, the H plus, is eventually going to join with water to form H3O. So that's why that's here. But this is also used in the same sense as hydrogen. So when you see this, just think hydrogen ion. So I've got hydrogen ions here and hydroxide ions there. So here, this is saying we have H plus in a bracket equals 10 to the negative 7. So the brackets just mean concentration. So the concentration of the hydrogen ions, H plus, which again, remember are these guys, is 10 to the negative 7th. And down here, the concentration of the OH negative or hydroxide, just these guys, is also 10 to the negative 7th. So if we multiply these two figures, 10 to the negative 7th times 10 to the negative 7th, we get a total ion concentration of 10 to the negative 14th. Okay? Now, acids and bases are going to change those concentrations if we add them to a solution. Acids are going to make the concentration of hydrogen ions higher than the concentration of hydroxide ions, while bases are going to do the opposite. They're going to make the concentration of hydrogen ions lower than the concentration of hydroxide ions. Now, let me just throw in a reminder here that we're dealing with a negative exponent. So we've got 10 to the negative 7th. So that means that if the concentration of one of these ions increases, of course, this figure is going to become greater. But since it's a negative exponent, it's going to look like it's getting smaller because this small number up here is going to be going down. So what do I mean by that? For example, let's say that we add an acid to water. That's sitting in equilibrium. So again, here I've got my glass of water, and I'm going to add H2SO4 sulfuric acid to this water. So once I add this H2SO4 to the water, it may change that hydrogen ion concentration from 10 to the negative 7th to, let's say, 10 to the negative 4, okay? Because we're adding hydrogen ions. So we're increasing the concentration of hydrogen ions in the water. Okay, so I've got that written out here. So the concentration of hydrogen ions has gone from 10 to the negative 7th to 10 to the negative 4, okay? Now, of course, if these were positive numbers, positive 4 would be less than positive 7, but these are negative numbers. So -4 is greater than -7. So this shows an increase, okay, not a decrease. So the concentration is increased. All right, that may be kind of basic, but I just want to throw that in there. Just make sure you remember that you're looking at a negative exponent. So if it's increasing, then the number behind the exponent is going to become smaller. If it's decreasing, then the number behind the exponent is going to become bigger. So if I add those hydrogen ions and the concentration of the hydrogen ions increases to 10 to the -4, that means that my hydroxide concentration is going to decrease to 10 to the -10. Okay, so if we multiply that, 10 to the -4 times 10 to the -10 equals 10 to the -14. It's always going to add back up to 10 to the -14. And another just mathematical note to remember, when you're multiplying numbers with exponents, you have to add the exponent. So you add -4 plus -10 to get -14. What about if I add a base to water or some aqueous solution? So again, I've got a glass of water, adding sodium hydroxide, which is a base. Now, let's say we add this base and that increases my hydroxide concentration. We go from a hydroxide concentration of 10 to the -7th up to 10 to the -6, okay? That means my hydrogen concentration is going to decrease from 10 to the -7th down to 10 to the -8th. Remember, -6 plus -8 gives -14. All right, now let's do a little practice just to make sure you're with me. Now let's say I've got another glass of water here and I add HCl, I'll give you a hint, hydrochloric acid. I add that to the solution and the concentration of one of the ions changes from 10 to the -7th to 10 to the -2, okay? Now which ion changed from 10 to the -7 to 10 to the -2? Was it the hydrogen ions or the hydroxide ions if I add HCl to the water? And the second question is, what will the new concentration of that other ion be? So if this ion here went from 10 to the -7th to 10 to the -2, first of all, which ion is that? Okay, and then secondly, what would the concentration of the other ion be if this one is now 10 to the -2? Let me know in the comment section below. Okay, so now that we've looked at how an acid or a base can move an aqueous solution out of equilibrium, let's go back to pH. Now, pH is really just an easier way, according to scientists, to write out the concentration of an ion. Now, officially, pH is the negative log base 10 of the hydrogen ion concentration, okay? So what does that look like? It looks like this. The pH equals the negative log of H plus, and you'll usually see that in brackets. Again, the brackets mean concentration. So if you see something in brackets in chemistry or biology, it's usually talking about the concentration of whatever is inside those brackets. Now, don't be afraid of the log and the negative signs and all that, okay? Like I said, you probably don't need to know the background mechanics of the formula, depending on what level of biology you're in. And what is important for us to know is that this is actually the log base 10 of 10, okay? Now again, I'm not gonna go into all the math of that, but essentially the log base 10 of 10 makes for a really easy equation. It's pretty much gonna be multiplying a number by 1. So that means that the pH is going to equal the exponent, the little small number up top. Whatever exponent you have for your hydrogen concentration, that's gonna be the pH. So let's go back to water to see what I'm talking about. Now, remember I said that at equilibrium, the concentration of hydrogen ions in water is 10 to the -7. Now, if I plug that concentration into the equation for pH, I get pH equals the negative log of 10 to the -7. Now, again, for reasons I'm not going to go into here, we can cross out this log and this 10, which simplifies the equation down to pH equals -7. Now, the only reason I have this -7 in parentheses is just so you can easily see that there are two negative signs, okay? So we multiply two negatives, because it's essentially -1 times -7. That's going to give us a positive number, so the pH is going to be 7. So the pH of water or some other aqueous solution that's at equilibrium is 7 because the concentration of hydrogen ions in that solution is 10 to the -7. Now, what happens if that concentration increases to 10 to the -5? The pH will then be +5. If the concentration decreases to 10 to the -12, the pH is going to be 12. So that is pH made easy. pH is going to be the same number as whatever little number you've got up here, your exponent. And the pH is always going to be a positive number because the concentration number is always going to be negative. So then we'll get a negative times a negative, which will give us a positive. Now, notice that the pH is not directly related to the hydroxide concentration. We don't have hydroxide anywhere in this equation. It's based only on the hydrogen ion concentration, hence the H in pH. But we already figured out earlier how to calculate the concentration of one ion if we know the concentration of another ion. And we can do the same thing. We can calculate the concentration of the ions as long as we know the pH. We're just going to subtract the number that we know from 14. So let's say we have a solution that has a pH of 8. That means that the concentration of hydrogen ions is 10 to the negative 8. Okay, so we take 14 minus 8, which is 6. So that means that the concentration of the hydroxide ions is going to be negative 6. Okay, so you can't plug in the hydroxide into your pH formula, but once you know the pH, then you know the concentration of the hydrogen ions. If you know the concentration of the hydrogen ions, subtract that from 14, you'll get the concentration of the hydroxide ions. Okay. Now we figured out how pH works. Let's go ahead and apply it to acids and bases. Acids make the hydrogen ion concentration in a solution higher than the hydroxide ion concentration. So again, remember the hydrogen ion concentration is represented with a negative exponent. So if the hydrogen ion in a solution is increasing, because that acid is adding more hydrogen ions, so as that number is increasing, which is a negative number, the pH, which is a positive number, is going to be decreasing, okay? So if we go from a concentration of 10 to the negative 7 to 10 to the negative 5, the concentration is increasing, but the pH is going to go from positive 7 to positive 5, which means the pH is going to be decreasing. So the higher the hydrogen ion concentration, meaning the more hydrogen ions are being added to a solution, the more acidic that solution is going to become. Also, the higher the hydrogen ion concentration, the more hydrogens we're adding, the lower the pH is going to become. So that must mean that the more acidic a solution becomes, the lower its pH becomes. For bases, think the opposite. Bases make the hydrogen ion concentration lower than the hydroxide ion concentration. So as that hydrogen ion concentration is decreasing, the pH is going to be increasing. So again, let's say the concentration goes from 10 to the negative 7th down to 10 to the negative 9. That means the pH is going to go from positive 7 up to positive 9. So the hydrogen ion concentration decreased and the pH increased. Okay, so let's sum this up. The lower the hydrogen ion concentration in a solution, okay, the fewer the hydrogen ions there are, the more basic the solution becomes. Also, the lower the hydrogen ion concentration, the higher goes the pH. So it must mean that the more basic a solution is, the higher its pH is going to be. Now, here's the fun part here. Let's look at a pH scale to help us visualize this and make sense of what I'm talking about. Now, the pH scale, as you see, goes from 0 to 14. 7, right in the middle, indicates a solution that is chemically neutral. Okay, now let me just give a note here that being chemically neutral is not the same as being electrically neutral. When something is electrically neutral, that means that it has no net charge. That's not what we're talking about here. When something is chemically neutral, what we are talking about, that means that it has equal concentrations of solute, particularly in this case, equal concentrations of hydrogen ion solute and hydroxide ion solute. Okay, so this is where we find pure water. Pure water is chemically neutral. It has a pH of 7 because it has equal concentrations of hydrogen ion and hydroxide ion. Now, as the solution becomes more acidic, the pH can start to decrease from 6.9999 infinite 9 all the way down to 0. So as we see here, the pH is decreasing because these items are becoming more and more acidic. Now on the flip side, as we get more basic, the pH will increase from 7.0000, a whole bunch of zeros with a 1 at the end, all the way up to 14, okay? So notice our pH is increasing here as we're getting more and more basic. So let's just take a look at some of the items that we've got here. Citric foods and drinks are going to be acidic. whereas a lot of soaps and household cleaners and things like that tend to be more basic. All right, so take a look here, and based on what you see, what are some other items that you think may be acidic and some items that you think may be basic? Let me know in the comments below. How about look at some of the foods and drinks here. So we've got lemon, soda, coffee, tomatoes, we've got egg whites. So what do you think may be some differences in how acidic foods taste versus how basic foods taste? And let me know in the comments below, just so I'll know that you're with me. Now, here's one biggie that you have to know and remember about the pH scale. This is not a linear scale. It's a logarithmic one, all right? Now, what does that mean? Remember, the equation for pH is the negative log of blah, 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 blah. You don't need to know all that again, but you do need to know how that affects this scale, okay? So all that means when I say it's a logarithmic scale is as we're going from one number to the next, so 1 to 2 to 3 to 4, we're not just adding by 1, we're actually multiplying by the power of 10. We're not multiplying by 10, that would be 10, 20, 30, 40. We're multiplying by the power of 10. So 10, 100, 1000. Now, for instance, let's take a look at lemon juice, which has a pH of 2, and your typical soda, which has a pH of 3. Now, because the lemon juice has a lower pH, we know that the lemon juice is more acidic than soda. But just how much more acidic is the lemon juice than the soda? Well, our number changed by 1. We went from 2 to 3. So that means the degree of acidity changed by 10 to the power of 1, or 10. So that means that lemon juice is 10 times more acidic than your typical household soda, okay? That means that lemon juice has 10 times more hydrogen ions than soda does. Okay, now let's look at that same typical soda versus the acid in our stomach, and that has a pH of about 1, okay? So stomach acid is more acidic than soda. How much more? The number changed by 2. We went from 3 to 1. So that means that the degree of acidity changes by 10 to the power of 2, aka 10 squared, which is 100. So stomach acid is 100 times more acidic than soda. All right, now let's flip it and look at some bases here. Now we've got egg whites, which has a pH of 8. And then we can look at bleach, which is right around 13. Now, which one of these is more basic, the egg whites or the bleach? And how much more basic is it going to be? Let me know in the comments below. Now, just a small addition of an acid or a base can dramatically change the pH of any substance. Now, in terms of the human body, that can actually be pretty dangerous. Our bodies operate at specific pH levels, and different parts of our body operate at different pH levels. So even small changes can have drastic effects. So for example, here, again, the stomach acid has a pH of 1 versus our blood, which is closer to about 7.4. Now, if a person's blood pH were to change from 7.4, even by just a couple tenths down to 7.2 or 7.6, then they would be in acidosis or alkalosis territory, both of which are life-threatening. Get to the hospital immediately. Okay, so knowing that we eat and drink and we're exposed to so many different chemical substances with all different types of pHs, how can we prevent potentially life-threatening changes in our own pH, or in our blood pH specifically? Well, this is where buffers come in. Buffers are weak acids and weak bases that minimize significant changes in the pH. So basically what that means is a buffer can prevent large changes in pH. They keep the changes small. Now, thank God, our human blood has a natural pH buffer, which is called carbonic acid. Now, this is a weak acid, and all that means is that it doesn't totally dissociate or totally break apart when it's in water or some aqueous solution. So let's take a look at how this bicarbonate buffer system works. Now, if the pH of someone's blood begins to rise, meaning it's becoming more basic because for some reason the hydroxide concentration is rising above the hydrogen concentration, the carbonic acid will start to dissociate or break apart into the bicarbonate ion, HCO3 negative, and the hydrogen ion, H+. Now, these extra hydrogen ions are going to balance out that increased concentration of hydroxide ions. and bring the pH back closer to 7.4 where we want it to be. Now, what if the opposite happens? Let's say the pH is dropping. It's becoming more acidic because for some reason the hydrogen ion concentration is rising above the hydroxide ion concentration. All right, then we're going to see the reverse of this reaction. This is a reversible reaction. So in this case, the bicarbonate ion, the HCO3, is going to bind with the hydrogen ion. So we're going to get this here to go back to form carbonic acid. So this is going to eliminate the hydrogen ions that are floating around in the blood. It's going to bring that concentration down, which is going to raise the pH back up to 7.4. So this is a great buffer system, again, in our bodies. It can go one way or the other, just depending on what the need is. If we need to bring the blood pH back down to 7.4, the reaction will go this way. If we need to increase the blood pH to 7.4, it'll go this way. Well, that's it for today's video. I hope it was helpful for you. If so, then please leave a thumbs up in the comments section below. And if you have any remaining questions, then type those in the comments and I'll do my best to provide you with an answer. Thanks again so much for watching CCL Biology, that is Christ-Centered Life. God bless and bye-bye.